Welcome to Inverse and Operations of Functions. We're going to be doing problem number 32, 33, and 35 from chapter 1. So those are what I need you to write down for me in your math notebook, because these are considered class problems. Even though we're doing it via video at home, there's still sort of lesson and note-taking problems that should be in your math notebook. So let's get started. Our first little math notes section here talks about the inverse of a function. Another word for inverse is undo. And we practice this in Algebra 2. This is a procedure where we undo what has happened to the variable or the x. The notation for this looks like this. This is a regular function, and this is a function to the -1 power is what it looks like, but it does not mean inverse in this case. That's only for exponents. Whenever there's a -1 on a function like this, that means undo, not this. So let's take a look at this in the case of problem number 32. We're given a f of x, a function that says half of x plus 6. So what steps would we need to do to undo what happened there? So if the first thing happening was halving an x and then add 6, the opposite of that would be to subtract 6 and then instead of halving, the opposite of that is multiply by 2. So subtract 6 and multiply by 2. So how could we write that using the steps? Find an expression for that in this notation. So it would look like the function, basically that's saying the inverse of function f, function inverse of f of x. Well, we take our x, and the first thing we do to that is subtract 6, and then we need to multiply by 2. Not just the x, but multiply all of it by 2. So parentheses are necessary to be able to show that. Okay? Let's take a look at the next one. So we've got another section of math notes. This one is on operations with functions. Operations mean add, subtract, multiply, divide. So sum, difference, quotient, product. That's what we've got going on here. So if we say f and g are two different functions, we're going to define, this is what it means to add two functions together, this is what it means to subtract them, and so on. So if we take a look at this, the sum of f and g of x is the same as f of x plus g of x, and so on and so forth. So these mean the same thing. These two notations mean the same thing. And it's important to note in the quotient that you can never divide by 0. So this only works as long as the function g does not equal to 0. That's what that means right there. And so the product can be written like this or like this. Okay, it says you can also compose functions. This means that the output of one function becomes the input for another function. This is written as f of g of x. And when that's written out, they sometimes write this f of g of x. And it looks like a tiny little O. And so people sometimes say fog of x because it looks like the word fog. But it really means f of g of x. The function of what you would get if you did g of x is what that is saying. So here's an example. If we've got these two functions here, and the first one says f of g of x, that means we take and plug g into x. So function g is then put into where the x is. And for the second one, that one is the opposite of that. So this one means g of f of x. So that's taking the output of f of x and putting it into g. So you take f of x, which is this, and plug it in for x in this function, and this is what we end up with. So we're going to practice that with the next problem. All right, so we've got these two functions. This is g of f of x and this is g of x. This says find f of x plus g of x. So you take the function f of x and we do 3x plus or minus 5. That's the f of x, and we're going to add g of x, which is x squared plus 2. Okay, so look at this. How can we simplify? Well, we just combine like terms, basically. Our largest term, as far as degree, is x squared. Then our next one is 3 to the x. And then we can put the two numbers together and we get minus 3. So here's our simplified result. When we do the next one, it's got an f of x next to a g of x. This means to multiply, find the product of. So we're going to end up doing 3x minus 5 multiplied by x squared plus 2. And in this case, we're going to need to distribute or use a generic rectangle to organize this. I'm going to go ahead and show using a generic rectangle so we can get a nice review of that. So we're going to put this on one side. How about we do 3x minus 5 across the top and x squared plus 2 down the side. Multiply these together and we get 3x to the third power. Negative 5 times x squared goes there. 6x for this box, and negative 5 times 2 is negative 10. And we combine all of our like terms, and so the final result for b ends up being, there are no like terms, so we just put it in descending order of degree. And there we have the result for b. All right, now moving on to c. This says f of g of x. So we're going to plug g of x into f of x. So this means we're going to take all of this, which is g of x, and we're going to insert it as the argument in for x in f of x. So it's going to look like 3 times, instead of x, all of the g of x stuff. X squared plus 2. And then continue doing this part, minus 5. And we can leave it like that, or we can simplify by distributing. If we simplify by distributing, we get our 3x squared. 3 times 2 makes 6, then minus 5. We get 3x squared plus 1 as a final result. All right, now for D. This one's the reverse. This time we're going to put f of x, oops, I erased a lot. We're going to put f of x in place of x in function g and expand that. So I'm going to write down function g right here, which starts with x squared, but the x is going to be replaced with the function f. So we get this, and that is all squared, and then plus 2. So we need to simplify this. To simplify this, again, FOIL generic rectangle. I will go ahead and just do a FOIL type strategy here. 3x times 3x, 9x squared. This ends up being negative 5 times positive 3, negative 15x, and then there's 2 of those, so negative 30x. Negative 5 times negative 5, positive 25, plus 2. So we have 9x squared minus 30x plus 27. All right, last problem. All right, this is a pre-problem for calculus, something that we're going to be doing a lot of. It's going to give us a picture of a graph showing how area can represent miles per hour and time. So we're looking at a case where Megan went walking for 2 hours. She walked at a steady pace of 3 miles per hour. So the first thing, how far did she walk? So let's take a look at that. For 2 hours, So I'm going to label it like this, 2 hours, and put it over 1 so we can make it look like a fraction. We multiply that by 3 miles per hour. So we've got 3 miles per, the divide bar is the per, 1 hour, 3 miles per hour. So when we multiply this, units can simplify just like variables. And what we're left with is 1 on the bottom, and across the top we multiply 6, and we have 6 miles is how far she's gone. Now step back and think about that. Does that make sense? 3 miles per hour for 2 hours? Yeah, 6 miles is how far we traveled. So part B says make a very careful graph of this situation. So here's a couple of axes. We're going to label the horizontal axis in hours, and this is going to be miles per hour. So we had 1 hour, 2 hours in our trip, and then here's 1, 2, 3 miles per hour. 1, 2, 3. So if we take a look at all of that, what's the area of this? Well, 6. 2 times 3 is 6. In part D it says divide the rectangle into 6 smaller pieces by drawing vertical and horizontal lines at the markers. So can you see each mile? Here's 1 mile, 2 miles, 3 miles, 4 miles, 5 miles, 6 miles. The area actually shows the answer to the problem. Pretty nifty. Okay, we're done. Thank you. See you next time.